Before I get started, like, how many of you have ever heard AutoML? Like, okay, that seems a reasonable crowd. So, so this is the overview of the talk. So, firstly, like, I'm going to talk about the motivation for AutoML, and specifically talking about what's the usually development flow of deploying an ML solution, and then talk about one thing called black box optimization, which is the very centerpiece of AutoML. And then a specific technology called neural architecture search, which is creating a lot of breakthroughs in the field of AutoML and also advances and challenges. So I'll try to keep the talk really high level, try to have less formula as possible so everyone could follow, since this is like the third week of the ML class? Third week, okay. So motivation. So what a usual ML development process look like? So usually, so I at Google, when I started working with product teams like Google Play, the Android store, or like shopping on different ML problems. So we usually go this thinking process like, firstly, we define the problem, and then we collect the data and try to engineer the features, like people do Kaggle competition. And then we work on together to improve the model or selecting the model or algorithm that we want to tackle the problem. And then we go like extensive tuning and experiments, and finally we launch the product or the ML solution. So, so do these terms look familiar to you, like feature engineering? Have you done any feature engineering before? No? Okay, so we'll talk about it more. So, because this exercise is to help us to realize like how complex and how much ML expertise is needed to develop an ML solution, and why like AutoML will be important. So then like the very first step of developing an ML solution, like problem formulation. So problems you ask yourself before you try any model, before you try any data. So what's the goal of this ML model? And also like what's the metric to evaluate this model? So for example, like if you want to build a video recommender on YouTube with the goal to increase daily active users. So then you should ask yourself like, what model I should be building, like how I'm going to evaluate the effectiveness of this video recommendation model. So can it be the click ratio? Meaning like if I show this video to a user, how much likely I'm going to click it? Or can this be like the watch time? Like how many hours users are going to spend on watching the video on YouTube? Or like number of videos watched for a single user after I have this machine learning video recommendation model. So this is really important because many of the applications, without knowing what we want to evaluate, okay, many of the cases like without knowing what you are going to evaluate, your real metric, which is the daily active user, your model will fail to learn very well that correlates the real metric you care about. So for example, these three metrics here, like they are seriously flawed, or they are flawed in some sense. Like, although you could build a really good ML model to predict these, but they sometimes like will fail to increase your daily active user of YouTube. Like for example, click ratio. Like if you just recommending like cute animals, like cat videos to everyone, I believe like the click ratio would be really high because people just like to click this, we call clickbait. And also watch time. Like, you know, like on YouTube, there are those videos that are really long, which is like background music help you sleep. Like usually this is like several hours. If you try to like recommend this kind of video, like your model will learn very well. Like you do increase the watch time, but I think you lose a lot of users. And also number of videos watched, like that maybe prefer like short videos. So this is a step like involves a lot of product insight and ML expertise. But I would say like this is more the emphasis is on product insight, like knowing what you are going to evaluate. And ML expertise only helps like whether this metric is measurable or like, can be formulated as some objective function you can optimize. And then we have the feature engineering part. So feature engineering meaning like when I collect the data, how I'm going to massage the data to make the best use of it. So do any term here look familiar to you? Like, okay. So, so for feature engineering, you got a lot of choices, like data cleaning, removing outliers, meaning like because many of the machine models are statistically inspired, you want to remove outliers to focus on the like the core data that follows some distribution, or like missing values, considering like your data is survey data. Like when you do survey, you skip a lot of questions. But if I'm going to train an ML model, how I'm going to deal with the skipped questions people leave on my survey data, and also deriving features. And the last two are pretty are currently receiving a lot of heat in the deep learning era. One is feature representation. So Andre just mentioned like you could have distributed representation of text. Like remember the word embeddings. Like that's one way you represent your text feature. And also you could represent a spec of words, which is just a set of tokens as it is. And also data augmentation. So if you look at a specific example of feature engineering, like it's really making a difference in image classification. So image classification is the task, like you're given the raw picture, raw pixels of an image, and you try to predict out of like 1,000 classes, like which class this picture is about. So people found out that just randomly you augmented the input image by either like cropping it in the center or rotate it a little bit or like just flip the image. You can learn like much stronger image classifier that generalizes very well. So for example, here on the right column is some policies people learn automatically to augment the images. And you can see like the error rate drops like by 1%, which is pretty huge. Like you can already publish paper within results like this. And then like when you have your data, you have an idea like what you want to formulate, and you have an idea of what feature processing, feature engineering you want to have, and then it's a time to choose the model. So so how many models do you know at the moment? Like, just name some, like name anything you know, like any machine learning model. Least squares. That's a very reasonable one. Anything else? Support vector machine. That's nice. So so there are definitely more than two models in the real world, and you're not going to learn all about it in the future, but definitely like if you dive into the machine learning literature, there are just thousands of them. And then like choosing a different model and algorithm is very important, and also it really depends on your problem, like whether you want the model to be iterable, meaning like if I'm going to present the model to someone like doing business, can they understand what the model making predictions based from? And can we explain the predictions from the model? And also serving constraints, like if my model is going to deploy it in a mobile phone, like probably you don't want to train like very large models. And also privacy and data availability, meaning like if you're going to train a huge neural network, and with only like a few hundreds of data, probably you're not going to train it. And also here is an example of deep neural networks. So deep neural networks are currently very hot, like in the era of deep learning. And the model architecture, meaning like how the deep neural network are constructed by layer by layer. So here each row is an architecture. So that's actual model people use in the real world among the year of 2015. These models are used for image classification. And you can see like each box is called a layer. And different colors stands for different transformation functions. So if you are, and edges meaning like edges shows like how these layers are connected. So you have your input on your right, which is raw image, and going through like this huge convolution of different functions. And then it gives you the 1,000 classes you are going to classify the image into. And FYI, like these models are all built by ML experts. So, which itself is very amazing. But if I'm someone like without any ML expertise, or even with ML expertise, like how do I know like I'm going to apply like 6 layers of convolution, which is the pink or purple boxes in the first, and then like several boxes later, like you just have no idea how you are going to do that. So this probably is a step like AutoML could come in and solve this problem, like automatically finding this very complex structure of how you like stack your layers into a deep neural network. And finally, when you have the model, you are going to tune the model, which is the actual training, like thinking about the case like you are going to give your data, you are going to train a least squares. Like that's the few steps. Like so training a least square may be relatively fast, like you could train it under 1 minute, something like that. But in real world, like imagine you have like billions of videos on YouTube, like trying even least squares with different hyperparameters would take you days. And then like this becomes a very computation expensive process. Like I want to enumerate all the different hyperparameters like the learning rate and regularization and like what optimizer I'm going to solve my model. And these hyperparameters also matter a lot. Like if you are careless, like choosing your hyperparameter or got unlucky, like you have different learning curve. Like the ideal learning, so here is an example of like comparing different learning rate. The ideal learning rate, as the learning, you have more steps, your objective function decreases smoothly on your test set. But if you're choosing like the wrong learning rate, which is very often in deep models, you're probably going to like converge too soon. For example, like the black circle, black line, or you're not even going to converge, like in the gray line. So a lot of words on how complex currently it is to develop an ML solution. So currently, a ML solution is like ML expertise, like knowing different pieces of the ingredients, and plus the data and computation. So the problem is, can we turn this into solution equal to data plus 100 times computation? So think about the case like computation would be only cheaper and cheaper in the future. But ML expertise, like just to train a ML expert, you need to like send them to college, and then you need to have like several years of industry experience or academia experience to really know like the ML problems. So I think that cost would relatively remain the same. So you probably want to like convert these ML expertise and trade it off for computation budget. So we are going to talk about technology. Any questions? No? Yes?
About choosing the model for like the architecture layer.
Yeah.
So randomly or starting from some previous works and adding some more layers and hoping to get the best. This is the usual way to build, for example, an architecture.
Yeah.
Speaking about the convolution neural
Uh-huh.
Is it?
Yes or no? So the question is, so because in this graph you are seeing like stacking of different layers. It's common to build new architectures like, okay, this has like 100 layers. I'm going to just add 10 more layers on top of it. Is it the way we build new architectures? So I think for like experimental project, that's yes. Like that's also a new kind of architecture, new model. But unlike, I think in the academia, like a serious research, that side, like that's usually like not considered like core research, at least in top conferences, unless you really got very nice results. Okay, so we are going to talk about technology. And let's start with the simplest AutoML technology, which is a script. If you read a script, it's fairly simple, like consisting of 3 for loops. My first for loop is like I choose a feature engineering function, and it's among like all the feature engineering functions available. And the second for loop, like for all the model architectures, I choose a model. And then third for loop, choosing different hyperparameters. So this is really straightforward, right? Like if you think like this script is straightforward, raise your hand. Okay, good. Yes, it is very straightforward. So the question is, can we do better than this for loop to automate the process? By the way, like this paper reference is wrong, so nobody published a paper based on this 3 for loops. So the question is, can we do like better than for loop to automate this process? So to understand that, we need to understand like how these 3 for loops are these different ingredients interact with each other. So for example, how parameters, hyperparameters, and the model interact each other. So if you write down what we are going to optimize, actually we have an objective function, which is f of x, and then we want to evaluate the performance on a specific model trained on a specific hyperparameters. And the parameters are a result of training with the model and the hyperparameters fixed. So, so in the least square case, like you only care about the parameters. And we say like it has an analytical form because you can explicitly write down your least square loss function and do like optimization based on it, like either get a gradient or get a closed form solution. But for the model and hyperparameters, usually you don't have this benefit. Like you cannot write down the model performance as a function of hyperparameters or your model structure. I mean, if you could, then it'll be perfect. Then you could use a lot of tools to derive the gradient and solve it. So for something we have analytical form, we use SGD, which is, we often use SGD, like called stochastic gradient descent for optimizing parameters, and we use GSD for model and hyperparameters. So it's a common joke when I was a student. Do you want to guess like what is GSD? Okay, I think I hear it from somewhere. Like it's graduate student descent. So you just assign the work, like you parallel your for loop to many graduate students and then let them do the work because every training to get the parameters is so expensive. So how do we solve something without an analytical form? So actually in the academic, this is a class of problem called black box optimization. Like you're going to try to solve the optimization function, like given an x that maximizes f of x, but you do not know like the function f of x itself. So what you can only do is you give the input x and get the results, get the value evaluated. So for example, something half analytical form is like a linear model. You can derive gradients and using the standard optimizing tool. But obviously, like, for the question like model architecture and hyperparameters, we don't have this good benefit. And indeed, in black box optimization, typically there are very two straightforward and simple methods to try. One thing is called grid search, the other is called random search. Like grid search, you so for example, here you are going to optimize a 1D function. The orange dot is a value you try, and the gray dot is the actual value, like you feed this to the black box function. So grid search proceeds as like you have like several candidates in mind, and then you feed them to your black box function f of x, and you get a bunch of results. And then you think from the results you get, you take the maximum. So in this case, like you take you take this value of x, which you think like can maximize the curve. So in the real, so this picture is just for illustration. So in real life, you don't know like how your f of x can be written as this line. You don't. What you get is just the dots there. And so random search, it's similar spirit, but every time you sample from different value of x, and then compare the best fx you have sampled, and you use it as a way to do optimization. So do you have any questions? Is this clear? Like if you think grid search and random search are straightforward, raise your hand. Okay, pretty good. Yes, they are very straightforward. And then things becomes a little bit complex when you go to higher dimension, because you could still do grid. So here, like I give an example of a 2D function. You have 2 dimensions, x1 and x2, and then still like the line is the function value. So on the left hand, you do grid search. You sample every equal space of x1 and x2, and actually, like as you see in this graph, like on the dimension of x2, the function value changes very little. So it's actually a dimension that fx is very insensitive about. But if you still do grid search, you just wasted a lot of spaces, like trying to get the function value in this area. But for the random search, it's a little bit better. In the case like it won't waste so much time on grid search every possible spaces, and you can see like these random dots here, and it has more chances to exploring different values on the x1 dimension, which is where the function value changes more as you change it. And then the ideal case is how can we do things smarter than grid search and random search, meaning like we learn from trials to sample more efficiently. So if our algorithm, like the black box optimization algorithm, is not smart enough, after it samples something have different value on the x2 axis, it'll know like, okay, it's meaningless to changing different values on x2. I'll try to sample on x1, which is more efficient to solve the optimizing problem. So efficiency is measured by number of trials I try on this, on probing this 2D spaces. So think about this ideal case. It's more like you have 2 research directions, and if you do like GSD, graduate student descent, if you have a really bad advisor, it'll just let you try every combination. So ideally, you want a very good advisor that has a very good prior knowledge. Like after you report to him like 2 trials you have tried on his idea, it didn't work, and then it'll probe you, it'll show you like very promising research directions. So this is also kind of black box optimization, because we don't know like whether our whether certain research direction would work or not. So let's link this back to the search space of AutoML. So in AutoML, 2 important search spaces are like hyperparameter and the model. So we here has a different terminology, like we have a controller, which is something that proposes a trial, and then fx is if the value of the function is obtained by training the machine learning model of the specific hyperparameters and the model architecture. And this is what you get from training and evaluating on your test set. Is this clear? Like how black box optimization relates to the AutoML problem? Questions? Okay, so then we are going to talk about one specific technique called neural architecture search, which is for optimized to finding model architecture automatically. So in a nutshell, like neural architecture search, NAS, is just a forward and feedback system. You have your controller, which is a machine learning model called RNN. The job of this controller is to propose a different model architecture. And then on the right, you train this model architecture we call the child network. And with the architecture A, the controller proposes, and then you get the accuracy R. And then you feed this accuracy with the trial to your controller, and your controller update it based on the feedback it gets and try to propose better architecture to try it later. So eventually you would imagine like my controller starts to propose better and better architecture, and the architecture automatically found just become better and better. So how it actually works in practice. So, so here let's take an image classification model together. On the left-hand side is the model architecture. Remember the giant model, like many of the boxes we see in previous slides. So here we want to also define the image classification deep neural networks to follow some pattern. So each box is a pattern we call a cell. Each cell consists of different functions concatenate. Each cell consists of different functions applied and aggregate on each other. So we have two different kind of cell, like normal cell and reduction cell. So you can also think like we have two different colors of cell, cell A and cell B. And each cell consists of different operations we want to search, like different functions on the input. So on the right, here is an example of a block in a cell. So actually there are several ideas here. One thing is the cell. One thing is the cell, which is the yellow and purple box. And another concept is a block, which is something you see on the right. So usually we put 5 blocks in one cell. So each of them are repetitive patterns as well. So on the right, we see we constrained the model structure of a block looking like this. Like you take 2 inputs and then apply some function. It can be any functions available to search from this search space. And then we either concat or add the output of these 2 functions, and then produces a new hidden layer. So in this case, like what we care is about what inside the block, meaning like what's the gray box, what's in the gray box, what's in the yellow box, and what's in the green box. So our controller is try to propose better proposals for these boxes. Like, so it follows as this, like given the input, my controller first selects like the first hidden cell and then the second hidden cell. And then selecting the different operations I want to apply to the first hidden cell, and hidden state, sorry, not hidden cell. And then selecting the operation for the second hidden state, and then selecting the function to combine this hidden state. So, which is basically a way to sample different operations. With these operations, we can construct the block. So if you take a look here, here we have 5 blocks, and which is something sampled from the process. Does this graph make sense? Like the H is the gray box in the previous slides. So if you think, do you understand? Is this any questions? Yes. Oh, what is the hidden state? So the hidden states are so for the very first layer of so let's go back to here. So the question is, what's the hidden state? So hidden state can be either the raw input image or the state, the representation that Andre talked about in a previous cell. So here, like a hidden state can be the raw images if it is for the first cell in the normal cell, or for the reduction cell, it could be the previous normal cell or the previous two normal cell. So each layer, the activations in that layer is called a hidden state. Is it clear? So the process goes on and on, like controller proposes an architecture and then we evaluate. So we repeat this like 20K times and find the best model. So remember, like even with this, like training or evaluate one architecture involves a lot of computation just for training. And so previously, NAS proposed to find this cell architecture, like for image classification, but it can be, yes?
Before come back to the architecture producer RNA, you are
Yep.
actually training this output architecture and
Yep.
evaluating the
Yeah.
result.
Yeah.
Then based on the result, so at least one time you should train this architecture, right?
Yes, yes, yeah. So, so the question is, at least you are training two things in this NAS algorithm. First is your controller, and the second is the child network on the right. It's the architecture proposed by the controller. So they reinforce each other, like with a better model accuracy. We know like how the controller are going to explore this search space, and then with better architecture, we just get higher accuracy. So let's go back to controller in the large search space. So because if you remember what we started our lecture, we have feature engineering, we have model architecture and hyperparameters, how they fit this into this big picture. So actually, like you can have your controller sampling from different spaces, just not only limited to the cell structure. So for example, here you can firstly sample a module. The module here means like TF hub module that Andre mentioned, which is also when you sample module, you effectively sample a feature engineering function available. And then you could also sample like number of layers you have in your neural architecture and also number of hidden states in each layer. So that's the model part. And also you can sample from different learning rate and different regularization, meaning like you can also sample or automate the search in the hyperparameters. So this framework combines everything together to make it end-to-end. Like you could AutoML in the feature engineering part, the model searching part, and also the hyperparameter tuning part. And also here's an example like what the model find, what this automatic algorithm find, like this crazy structure network, which is almost impossible for human to design. And so just as I mentioned, like there is a lot of research on this field of applying neural architecture search or NAS in general, like in image classification, RNN cells, and also activation functions like designing, automatically looking for functions that are effective in neural networks, and also looking for like new optimizers and also image augmentation strategies, meaning like how much you want to rotate your image and how are you going to crop your image, like searching for strategies to make a combination of different image augmentation. And we can combine transfer learning with neural AutoML, like meaning like, for example, training one task already taking a long time for the controller because every time you need to explore, run the whole training and run different configurations. But if I was given a new task, I don't want to start from scratch. So the idea of do multitask transferable controller is like I try to reuse the controller when I train like different tasks, like classifying sentiment in sentences and classifying like classes of different newspapers. I do this all together with one controller, and which with the goal to save resources and try to learn better model and on the end task. Yeah, and there are examples like why this is awesome, and I'm going to skip this. Yeah, so for AutoML, I hope the takeaway here is like what the ML process is and why it's complex and involves a lot of ML expertise, and also the basic concept of black box optimization and the NAS algorithm. So for AutoML research directions, one thing is like how to have like lifelong agents, meaning like given a new task, I could continuously train on my old controller to propose new models, but sharing the same controller. So it's more like you have using new tasks to train our ML expertise. Like the more ML tasks the expert is given, like he is able to propose better and better models. And also multiple objective and end-to-end AutoML, like meaning making AutoML end-to-end, like to really achieve like you just gave me the data and I could give you the full ML solution. And also a lot of research is on the direction to make AutoML more efficient, because currently like every time my controller proposes something to try, it involves training from scratch. And we're trying to make it better. Yeah, that's the end of the talk. Thanks. Questions? Questions? Oh, yeah. Yeah, AutoML mostly for offline training.
If it's for offline training, why do you care about latency?
Okay, can you say it louder?
If it's an offline training, why do you care about latency that much?
So the question is, if AutoML models are used for offline training, if it's for offline training, why do you care about the latency so much? So, so here's the thing, like in the initial paper, in the NAS paper, to find this architecture automatically, it involves like hundreds of GPU train for 4 days. So latency definitely matter, because if you are individual who don't have a lot of computing resources, it'll going to take half a year to get a model.
That's more about throughput, right? You want to get that's more about throughput. You want to get the most out of it.
Yeah, yes. You want to improve the state of the art. And also another latency factor is depends on where you are going to serve your model. So if you are going to serve your model, like put the model into your mobile devices to recognize faces, for example, So you want your model to be trained. You want your model to make predictions really fast, and you care about the latency of the model you find to have low latency.
In the case where you actually have the trained models installed on your local phone,
Yeah.
the phone will only be responsible for the inference part, it's not for training.
Yeah, it'll be for inference part. Like smaller model would have, or like specific encoding of the model, saying like you just use like low 8 bytes instead of the 4 floats. It will make a difference in inference. And you can also search this and put it as a constraint in your NAS algorithm. Yes.
What about the future engineering tools that is applicable for a specific model? How are the restricted size? There should be like, it can be 3 by 3 filters, 5 by 5 filters, 10 by 10 filters, like too much. How are you restricting?
So currently, many of the where you search your model architecture, like things you put in the cell, and still like ML expert inspired. Like you still have a pool to search, and the search space is defined by like ML expert. Yeah, but that's better.